Today we're going to talk about Green's theorem. So let's go ahead and take a look. What I want to do to begin with is to give you a little bit of a background as to what motivates this. So let's think back to the fundamental theorem of line integrals. Last week we worked on the fundamental theorem of line integrals, and we said that it was kind of like an extension of the fundamental theorem of calculus. Okay, it took the idea of integration, except over a line, and did a fundamental theorem of calculus-like thing to it. What we want to do today is the same idea, except instead of taking a regular integral or line integral, we want to apply it to a double integral. Okay, so let's look a little bit more specifically back at the fundamental theorem of calculus. The fundamental theorem of calculus says if we want to take an integral from a to b of some function, look at the antiderivative at the two endpoints. Okay, so we only need to know the antiderivative at the two endpoints in order to know the value of that integral, adding up the whole thing all along. The fundamental theorem of line integrals is similar. We take the integral of some function dr, and we can evaluate that integral by looking at its antiderivative in a sense, right? If I think of f as being my function, the gradient of f is kind of like a derivative, just like if I think of f here as my function, it's the derivative that we want to look at. Okay, so I can think about looking at the antiderivative just at the two endpoints. Okay, so Green's theorem is going to work the same way, except we want to look at a two-dimensional region. So we don't have a line, right, or an interval that has two endpoints. We have a two-dimensional region, so the boundary of that region is going to be a curve instead of just 2 points. Okay, but we want to sort of look at the same idea where I look at kind of like the antiderivative on that boundary. Okay, so just to give you a heads up, we're going to have two forms of Green theorem, a circulation form and a flux form. Okay, we're going to start with the circulation form, and we're going to think of that as being kind of like the main form that we work with. And it's going to relate a double integral over a region to a line integral, okay, over a closed curve. So here's the theorem. We want to start with a an open simply connected region, right? So to give you an idea, we're starting with some region R that we're integrating over. Okay, suppose that C is the outside edge of this region. So that's the curve C. Okay, we want it to trace the outside counterclockwise. Okay, then let f be our vector field. Then if I want to integrate f dot dr, we want to, again, to think about this as like a fundamental theorem, I want to think about like an antiderivative of f, or think of the f as the derivative of something. Okay, so if I want to think about the derivative of f, I can think about its partials, right? So here, the thing I'm integrating is like the derivative of f. And it's not, we don't have like one derivative, so this is where we get different forms like a flux and circulation form. But we're going to look at the derivative of f in some sense, all right? And that's kind of the idea. So that's kind of like an antiderivative, but not exactly. It gives us a little bit of the spirit of the fundamental theorem. Here we connect a double integral to a line integral, and we've written the same line integral two ways, right? These, we've said before, are the same. Okay, and so my double integral, I can go back and forth. Let's look at an let's look at this in a picture. So here's a visualization. Think about my region, right? In this case, we've called it D, and C is the outside boundary of that. Okay, so to calculate circulation, what we're doing is we're saying at every given point on the boundary, how much of the vector field is moving along the boundary or tangent to the boundary. okay, and adding that up. So that's the line integral. And then that's going to be related to taking the double integral, so adding up the amount of vector that we have through all of the points inside the space, right? So we're relating that double integral over the region to the line integral along the boundary. Okay, let's look at an example. So here's my line integral, and so it's kind of given in this p dx q dy form. So I can see here that the p is x squared y, and the q is y minus 3 dy. The region that we want to integrate over, right, I'm starting with a curve that has vertices 1, 1, 4, 1, 4, 5, and 1, 5. So this outside part here, oriented counterclockwise, would be like my boundary curve. Okay, and I can think of the inside as being my region R. Okay, so then Green's theorem says, okay, this line integral over C is equal to the double integral over R of qx minus py. Okay, so I have to do a few things here to set up this double integral. I need to compute what is py, so I differentiate with respect to y. I need to calculate qx, so I differentiate the q with respect to x and just get 0. Okay, and I also need to figure out my limits of integration. Since this is a rectangle, my x's are just bound between 1 and 4, y is between 1 and 5, so I don't really need to do any careful setup here. Okay, but typically with the double integral we have to figure out what are our limits of integration going to be. Okay, so now we can just integrate this away, and because all of this stuff with x's, right, the integral and all the function doesn't have any y's in it, you can think of factoring it out. So you could think of this as like the integral from 1 to 5 dy. Oops. I wrote dx twice. The integral from 1 to 5 dy times the integral from 1 to 4 of x squared dx. So we get 5 minus 1 times 1/3 x cubed from 1 to 4. Okay. And 4 cubed is 64 minus 1 is 63. Okay, times 4 gives me 252/3. Okay, so that's the value of our line integral. Okay, let's look at another example where we're not integrating over a rectangle. So I'm going to start by looking at this region I'm integrating over. So here we have a right triangle with vertices -1, 2, 4, 2, and 4, 5. Okay. So if I connect these points up, they look like they give me a right triangle, which is good. So it looks like it should look like. Okay, and once again, we have this setup where I have a p dx plus q dy. So I can change this integral along my curve C into the double integral over the two-dimensional region R. Okay. Right. P dx plus Q dy turns into a double integral of Qx minus Py. Okay. So once again, we figure out what is the Py. When I differentiate sine x squared with respect to y, I get 0. What is the Qx? When I differentiate 3x minus y with respect to x, I get 3. So when I subtract, I'm just getting 3 minus 0, or 3. Oh, and then let's figure out which way do we want to integrate. This we could set up as either a type 1 or a type 2 region. Okay, so I'll just set it up as a type 1 going up and down. So I want my y values to start at 2 and to end at whatever this line is. So I'm going to figure out the equation of that line. So the slope of that line, write down the points. The slope of the line is going to be 5 minus 2 over 4 minus negative 1, so 3/5. And then I'll just use point slope form of a line. Y minus 5 equals 3/5 x minus 4. Let's clean it up a little bit. Distribute. So I have 3/5 x minus 12/5, and then add 5 to both sides. So I get y equals 3/5 x. Negative 12/5 plus 25/5 gives me a positive 13/5. Okay, so my limits of integration for y are going to be from 2 to the line equals 3/5 x plus 13/5. And my limits of integration for x are going to go from negative 1 to 4. So I'm integrating dy dx. Okay. So this one I cannot split up into separate integrals multiplied like I did last time because they're interconnected here. So I integrate dy and I get 3y. Okay, so we plug in. So I have 3 times 3/5 x plus 13/5 minus 0. Okay, I'll distribute the 3. So we have 9/5 x plus 39/5 that we're integrating. So when I integrate, I get 9/5 times 1/2 x squared plus 39/5 x. Okay. And since we're running out of room here, I'm just going to compute this away really quickly. And I think I get 171/10. Okay. So we don't need to write down all of the arithmetic, but there we go. All right. We probably could have computed this as a line integral, but if I notice the individual pieces here, I would have had to parameterize these 3 lines separately. So first of all, it would have been 3 separate line integrals. And I would have had to find the potential function for this thing, right? So I would have had to do that process where we integrate, differentiate, integrate again, okay, and find the f that goes along with this, okay. And when I'm integrating sine of x squared, if I'm integrating dy, that's fine. If I'm integrating dx, I hope there better be an x on the outside, or I won't be able to integrate that. So this might have been a complicated or possibly impossible function or problem integral to compute as a line integral, but is very straightforward as a double integral. Okay, and sometimes things go the other way, right? Maybe it would have been a difficult double integral, and we could make it an easier line integral. So maybe we'll look at that next. Calculate the area enclosed by the ellipse. So if I draw this out to begin with, I'm starting with, oh, that looks more like a circle. Okay, that's kind of a terrible ellipse, but we'll just go with it. So I'm starting with an ellipse, and I want to find the area inside. Okay, so first of all, I have to figure out, does this even have anything to do with Green's theorem? How do I find area? There's lots of ways to find area, right? We could use a single integral, okay, underneath a function, or we could do a double integral over a region. And I think that's what we want to set up here, just to make this fit a Green's theorem type example. Finding the area of an ellipse is something that you probably did in Calculus 2 at some point. So we certainly don't need Green's theorem to do it, but we're just kind of making a connection here. So the area is going to be the double integral over the region R of 1 dA, right? That's something that we talked about before in chapter 5. I can compute areas by taking a double integral of the function 1 over that region. Okay. I'm not even going to bother writing down limits for R, because instead of doing this as a double integral, I want to see if I can write this as a line integral using Green's theorem. Okay, so let's back up a bit and look at Green's theorem. If I'm starting with a double integral, I can rewrite that as a line integral, but the function that I'm integrating in that double integral is qx minus py. So I know that qx minus py has to equal 1. That's not enough information to tell me what the p and the q are. What I'm going to do is pick a p and q that make that true. There are lots of p's and q's that make that true. So you could pick any one you want. I'm just going to sort of pick one, and it's kind of a standard p and q to pick if I want qx minus py to be 1. Okay, and the idea is, okay, I'll just make it so the qx is 1/2 and the py is negative 1/2, so that when I take 1/2 minus a negative half, I get 1. So if I wanted that to be the case, then the qx should be 1/2 x, or I'm sorry, the q should be 1/2 x, so that when I differentiate with respect to x, I'll just get a half. Okay, and the p should be negative 1/2 y. Okay, now I'm not saying that that has to be the case. That's not the one and only vector field whose difference of the cross gradients gives me 1, or sorry, cross derivatives give me 1. This is just one example that we can pick, and it's a nice simple one, right? So we're going to let f be 1/2 x comma negative 1/2 y. Okay. So then I can turn this from a double integral over R into a line integral over C, okay, of 1/2 x dx plus negative 1/2 y dy, where I have to have a parameterization of my ellipse. Okay, and if I'm looking at this, when I think about parameterizing an ellipse, I might say, oh, this is very circly. I might be tempted to, convert things to polar. Okay, so I think a common mistake that people might make, and most of the mistakes that you're going to make on this sort of thing are going to be on the setup, is to say, well, can I convert everything into polar? And you can, but what we're looking for is a parameterization. So if you convert to polar, make sure you're finding out, polar parameterization of the curve. So we don't want like x equals r cosine theta, y equals r sine theta, and then x squared over a squared plus y squared over b squared equals 1 becomes like an r squared cosine squared theta plus r squared sine squared theta. Okay, it's not that this is incorrect, but it's not finding what we want. What we want is, like an r of t thing, right? So I want to parameterize x and y by, think of it as some variable t. Okay, and it's very related, right? So what I can do is I could say, okay, maybe make x, it's kind of like a circle, so we'll use cosine theta and sine theta, but I want to scale them out, so the x's need to go out to a, so multiply by a. So I have a cosine of t, and the b's I want to rescale so they go up as high as, the y's have to go as high as b, so I want b times sine of t, and so that where t goes from 0 to 2 pi will give me a parameterization of the outside of the ellipse, going counterclockwise, just like we wanted. Okay, so then I can rewrite my integral. Okay, and now we see, oh, we made a little mistake here. Remember, f is p comma q. Okay, so the p is negative 1/2 y, and the q is 1/2 x. Okay, so our vector field f is p comma q, so negative 1/2 y, comma 1/2 x. So if I'm integrating, again going back, p dx plus q dy, we want negative 1/2 y plus dx plus 1/2 x dy. Okay, so when I want to convert this over now, I need to be careful that I'm filling in x, y, dx, and dy in terms of t, so I can write this as an integral with respect to t. Okay, so if x is equal to a cosine of t, then the derivative dx dt is a times negative sine of t, so dx is equal to negative a sine of t dt. Likewise, y is equal to b sine of t, so dy is b cosine t dt. So when we convert, I'm not only converting the x's and y's over, but I'm converting the dy and the dx as well. So we have an integral from t equals 0 to 2 pi, negative 1/2 times y is equal to b sine t, times dx, which is negative a sine t dt, plus 1/2 x, x is a cosine of t, times dy is b cosine of t dt. Okay, so before I start integrating, I'm going to simplify this a little bit. I'm going to factor. Both of these terms have a dt in them, so I factor out the dt. And they both have half, an a in them, and a b in them, right? Half ab. The negatives on the first term cancel, so I factor out 1/2 ab, and in this first one I'm left with sine squared t. In the second one, if I take out a half, the a and the b, and I also took out the dt, I'm left with cosine t times cosine t, or cosine squared t. Sine squared t plus cosine squared t is 1, so I'm just integrating 1/2 ab with respect to t from 0 to 2 pi. So I get 1/2 ab times 2 pi minus 0, or just pi ab. Okay, that's our integral. Okay. That means that we can now think of this as like a formula, right? I could always just find the area of a region by using a line integral now. Okay, so we can find area of a region using a regular integral. We can find area using a double integral. Right? We did that back in chapter 5. We did a double integral of just 1 dA. And now we can do an area using a line integral. Okay, now there wasn't some special need that made us find Green's theorem just so we could compute areas with a line integral. Okay, that's typically not going to be the easiest way to compute an area, although it might be in some cases. What we want to do is we want to think about making connections here. That's why we point this out. Okay, so we can relate a regular integral, double integral, line integral. They can all be interpreted as area, and so it really puts an emphasis on what exactly are we setting up, and that will tell us what something is computing. Just putting an integral in front of something doesn't really tell us what it is that we're doing. Okay, so if I pick the same setup that we just had, where f is negative 1/2 y comma 1/2 x, then the qx minus py is 1. So the area I know is like a double integral of 1 dA, which by Green's theorem we can turn into a line integral. Okay. So it gives us a way to compute areas pretty easily using line integrals. All right, let's look at an example of that. Instead of something that we already know the area of, right, like an ellipse, let's look at some weird shape and say, can we find the area enclosed by this? Okay, this would be a little bit of a nightmare as a Calc 2 problem, all right, a Calc 1 or Calc 2 problem, because although I have a nice parameterized curve here, I can't draw a nice like top and bottom function for this thing. We'd have to break it up into all sorts of pieces. The pieces wouldn't line up really nicely, and it's parameterized with trig function, so it would all look like a mess. Let's see what this looks like if I try to apply Green's theorem to it. So we want to find the area enclosed by this curve, and we're given a parameterization for the curve. Okay, so from what we just had above, we can say, okay, that area is going to be the double integral over r of 1 dA. Or what we just said is we can write that as 1/2 of the line integral along the boundary. Okay, of negative y dx plus x dy. Okay, and I already have a parameterization. That was the one thing that we were given. So I know what x is and I know what y is, right? So if we have x is sine of t times cosine of t, okay, I'm able to plug that in, but I need to find the dx. So when I differentiate, I have to use a product rule. The derivative of sine of t is cosine of t, and times cosine left alone, plus the sine left alone, times the derivative of cosine. So I have sine of t times negative sine of t. Okay, so dx is equal to cosine squared t minus sine squared t. Okay, Now there's some identities that you could use on that, but let's hold off and see what identity we might want to use once we see what this thing looks like with everything plugged in. Okay, so we're going to leave that like that for now. Let's write the y. Y is sine of t, so dy is cosine of t dt. Okay, so that part's not so crazy. All right, so we have 1/2 the integral from t equals 0 to pi of negative y, so I have negative sine of t, times dx, so that's cosine squared t minus sine squared t dt, okay, plus x, which is sine of t times cosine of t, and then dy, which is cosine of t dt. So let's see if we can clean this up a little bit. In the first term, I'm going to just go ahead and distribute. I have negative sine of t times cosine squared t. And then negative sine t times negative sine squared t is a positive sine cubed t. And then my last term is sine of t times cosine squared t. Okay. And now if I look at this, the first term, negative sine t cosine squared t, and then I have a positive sine t cosine squared t. Those just add to 0. So what I'm integrating is just sine cubed t. So I'm going to write that as sine squared t times sine of t dt. And the reason is, in order to integrate this, I'm going to want to use a u substitution. So I want to pick a piece for my du, right? So this, if I'm going to use a trig function like sine or cosine, then the du needs either sine or cosine on there. So I'm going to save that sine of t dt to be part of my du. So then if we write out what this is, right, if I want my derivative of u to be sine of t, right, to have a sine in it, then the u should be a cosine t, right? So then du is negative sine t dt. Okay, so if u is actually cosine, I want to take this sine squared and transform it into cosines. So we use our trig identity. Sine squared t plus cosine squared t is 1, or sine squared t is 1 minus cosine squared t. Okay, so now I can turn this into an integral with u's. When t is 0, cosine of 0 is 1. When t is pi, cosine of pi is negative 1. Okay. Cosine was u, so this 1 minus cosine squared t is 1 minus u squared, and sine of t dt is a negative 1 du. Okay. So I'll bring the negative out. Let's go ahead and integrate. I get u minus 1/3 u cubed, where u is going from 1 to negative 1. So then let's plug in. When I plug in negative 1, I get negative 1 minus 1/3 negative 1 cubed. And when I plug in 1, I have 1 minus 1/3 1 cubed. Okay. So this is negative 1. Negative 1 cubed is negative 1. Negative 1/3 times a negative 1 is a positive 1/3. Okay, here I have minus and negative, so plus 1/2. This 1 was cubed. That's still just 1. Minus 1/3. So many negatives. I'm going to be very careful. Okay, I'll distribute a negative half. Negative times negative is a positive half. Minus 1/6 plus 1/2 minus 1/6. So I have a half plus a half minus a sixth minus a sixth, which should give me 3, 6, 5, 4/6 or 2/3. Okay. So we started with having to find area of a kind of a complicated region, and we were able to compute it by converting it into a line integral because we had the parameterization anyway, and so the line integral was simple enough. All right. Now let's look at the other form of Green's theorem. This is the flux form. So this is still in concept the same idea. I want to turn a double integral over a region into a line integral, but this time we're converting between if I look back, right? Instead of my line integral saying how much of the vector field is moving tangent to my boundary curve, we want to say how much of my vector field is moving across the boundary curve, right? That's what flux is. So we're looking at an open, simply connected region with a boundary curve C, just like we had before, right? F is my vector field. Okay, then the integral of f dot n, right? Remember that n is a normal vector, right? So you can think of it as being perpendicular to the curve at every point. Okay, so the dot product is going to be how much of f is perpendicular to n, right? Or how much is going across. So that integral ds is the double integral, and it's kind of the same, but things are rearranged a little bit differently. Okay, instead of qx minus py, we still have these first partials, but they're not cross partials anymore. It's px and qy, and they're not subtracted. Okay, so you can think of it, now we're working sort of perpendicular, or what we're computing is sort of perpendicular to what it was before. So we flop the x's and y's and throw a negative on it, right? Okay, this form can be a little bit difficult to work with. The line integral dot n can be kind of rough. So this is typically used to go the other direction, go from something hard to something easier. Okay, so let's look at an example. And what we're going to want to do is move towards that double integral. So let's suppose that I have star region, triangle with vertices 0, 0, 1, 0, and 0, 3. Okay, oriented clockwise. Okay. In the theorem, this says that we want our curve oriented counterclockwise. And just for comparison, if I look back at the circulation form of Green's theorem, this was also oriented counterclockwise. So typically when we write Green's theorem, when I want to look at the line integral, we want to think of it always being oriented counterclockwise. Okay. Keep in mind counterclockwise, if I think of trigonometry and I think of my quadrants, all right, they go counterclockwise. Okay, so we try to stay consistent with things in math, and we say, all right, counterclockwise is the default direction. Okay, so here, if this is oriented clockwise, then it's backwards. All right, and that's fine. We can deal with that. Calculate the flux of this vector field f across our triangle T. So the flux is going to be the integral across T of f dot n ds. And I don't want to have to compute that, unit normal vector. Remember, that was a lot of work back in chapter 3. So what we're going to do is, after you compute that nasty thing, then you have to integrate it. Say, okay, let's instead rewrite this as a double integral using Green's theorem. Okay, so we turn this into the double integral over R. Okay, of px plus qy dA So our vector field F was PQ, so here this first component is P and the second one is Q. Okay, so Px is the derivative of x squared plus e to the y with respect to x, so I get 2x plus 0. Okay, Qy is going to be 0 plus 1. Okay, so when I add these together, I'm going to have 2x plus 1. Okay, and I need to now figure out my limits of integration. So we need to figure out, is this a type 1 or type 2 region? It would work either way. So I'm just going to go ahead and draw my rectangles. Think of them as going up and down. So I want to start at a y value of 0 and end wherever I hit this line. Okay. So the slope of that line is the changes in y over the change in x, okay, which is -3. And I can see the intercept is 0, 3, so I can just write y equals -3x plus 3. Okay, so my y values are going to go from 0 to -3x plus 3, and my x values are going from 0 to 1. So I'm integrating dy dx. Okay, that's a really nice looking integral, right? That should be no problem. So let's go ahead and integrate. In this case, if I look at the integrand, 2x plus 1, I'm integrating dy, so that 2x plus 1 is constant. So then I just get y going from 0 to -3x plus 3. So we say, all right, we go ahead and plug in. So I have 2x plus 1, and when I plug in, I have -3x plus 3, and then minus 0. So just write the -3x plus 3. Okay, before I integrate again, I want to clean this up. So let's go ahead and FOIL. So 2x times -3x is -6x. Okay, plus 6x minus 3x gives me plus 3x. Oh, I lost my squared. And then 1 times 3 is 3. Okay, so now we can integrate. So when I integrate x squared, I get 1/3 x cubed. When I integrate x, I get 1/2 x squared. When I integrate 3, you get 3x. So I get -2 times 1 cubed plus 3/2 times 1 squared plus 3 times 1. Now I plug in 0, they're all zeros. Okay, so I have -2 plus 3/2 plus 3, which gives me 5/2. Okay. Now, I made a big stink at the beginning of this about this being oriented clockwise. And when we use Green's theorem, remember it says counterclockwise. Okay, so what we want to do is just say the integral, remember the integral over c of whatever we like, is the opposite of the integral over -c. So if I want to traverse it backwards, I just throw a negative on it. Okay. So maybe backing up a second, the flux is this integral over t of f dot n ds, which is the opposite of the integral over -t. And so then we just say, okay, carry that negative with me the whole way down, and we get -5/2. All right. Now, while I'm looking at the conditions, one of the other conditions that we had was R is an open, simply connected region. And that's fine when we're creating a theorem. We want to make things nice and manageable so that we can, actually create our theorem and use it so it's not too complicated. But a simply connected region is pretty limiting, right? That means that the region can't have holes in it, right? So for example, this region is not simply connected, right? Because I have this region that has 3 holes in it. So if this is the region that I wanted to find a double integral over, that double integral would exist, but I wouldn't be able to use Green's theorem because it doesn't meet the right hypotheses. What we want to do is look at how could I use Green's theorem anyway? What could I do to be able to apply Green's theorem to something that has a hole in it? And the concept behind it is we want to divide this up into pieces, right? If I think about this as being a region with holes, and I say, well, if you just were to make some cuts in it, we could split it into 2 separate regions, okay? And if my boundary is oriented, suppose the outside is oriented counterclockwise, and all of the inside holes are oriented clockwise, then things line up correctly, right? Where my inside, the holes were clockwise, the outside was counterclockwise, and you can see that we're moving all in the same direction on each of these 2 separate pieces now. Okay, so I could take a region that has holes in it and just break it up into 2 separate pieces, and those regions do not have holes in them. So you can apply Green's theorem even if you don't have a simply connected region by imagining splitting it up into pieces. Now, depending on which way you're going with Green's theorem depends on how much work you have to do there. For example, if I want to take my region double integral over a region and convert it into a line integral, I have to work out these 2 separate line integrals, right, where they're parameterized each, separately, right, because they're going to have different directions. And to parameterize this is going to be a bit of work, right, because let's suppose I had a nice parameterization for the outside curve and one for each of the inside ones. Now one of my integrals has 1, 2, 3, 4, 5, 6, 7, 8 different pieces to it. So it'd be kind of a pain to go that direction. But it's doable. What we're going to do is we're going to look at the other direction. Let's suppose I want to calculate an integral of a line integral that's not a simply connected region, and I want to use Green's theorem. Right? So let's go ahead and take a look. Calculate this terrible integral where my region R is given by this annulus, right? An annulus is a disk with the center punched out, right? It's like a 2-dimensional donut. So this is our region R. Okay, it's given by the polar inequalities. R goes from 1 to 2, and theta goes all the way around 0 to 2 pi. Okay, so again, if I was computing this as a line integral, I sort of have these 2 separate pieces, so I'd have to create 2 separate parameterizations, and we've got a really messy function that we're integrating. So what I'm going to do is I'm going to use Green's theorem, okay, by imagining this as being split. The thing is, if I'm converting it the other direction, when I make these splits, on the top curve it's oriented this way, and on the bottom curve it's oriented this way. So when I make a split, I'm actually thinking of it as being 2 lines, one of them going this way and the other one going the other way. Okay, and when I integrate over those 2 lines, I'm integrating over the exact same curve, except my starting and ending is swapped. That means that one of those is going to be the opposite of the other, or when I add them, they add to 0. Okay, so when I look at a region with holes in it, okay, adding in these cuts is really just adding in 0. Okay, so in order to take my region with a hole in it and cut it into two, I'm adding in a bunch of pieces that add up to 0. Okay, all right. So I can take this integral and we're now going to skip the whole part where we split it and parameterize because we don't need those, and to say, okay, use Green's theorem to write this as a double integral over R. Okay, now what I have is this integral of p dx plus q dy. Okay, that fits this circulation form much better. So I'm going to turn it into the double integral that I get in the circulation form because that's sort of the beginning part that I have. Okay, I can identify the f a little bit more easily that way as opposed to being able to see what the f dot n is. Okay, so we're going to write this as qx minus py. Okay, where this piece is p and this piece over here is q. Okay, so py, if I differentiate sine x minus 1/3 y cubed with respect to y, the derivative of sine x with respect to y is 0. When I differentiate negative 1/3 y cubed, I'm going to get negative 1/3 times 3y squared, or negative y squared. Okay, if I take q 1/3 x cubed plus sine y and I differentiate with respect to x, the 3 comes down and cancels, so I get x squared, and the derivative of sine y is 0. Okay, so qx minus py is x squared minus negative x squared. I'm sorry, x squared minus negative y squared. Okay, and we'll leave this as a double integral for a second. The region that we're given was defined by polar inequalities, and that circles, right? Circle inside a circle. So this seems like it might be easiest to write instead of as a rectangular integral, right? Let's write this as a polar integral, right? So let's convert to polar. Okay. In polar, my limits of integration are given. R goes from 1 to 2, theta goes from 0 to 2 pi. Okay. In polar, we have x equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. Okay. Oh, I made a mistake. This is minus negative y squared. So I have x squared minus negative y squared, or x squared plus y squared. So my integrand is just going to become r squared. So I have r squared r dr d theta. So I don't have to, well, I don't have to do a lot of work here. I don't have to do any substitutions or anything. I do have to be careful, though. Remember that factor of r that comes out. So let's combine these together as an r cubed. I am able to use my shortcut, though. There's no thetas in here, so I can think of factoring this whole r integral out and get the integral from 0 to 2 pi d theta times the integral from 1 to 2 of r cubed dr. So we have 2 pi minus 0 times 1/4 r to the 4th. So we have 2 pi times 1/4, 2 to the 4th, minus 1/4, 1 to the 4th, okay, which is 2 to the 4th is 16, 1 to the 4th is 1. I think I wrote a half here. Okay, so 16/4 minus 1/4 is 15/4. So I have 15 pi over 2. Okay. Okay, so that's integrating a general region with holes in it, and that's Green's theorem.